Apologies if my voice is a little hoarse. I've been a little sick. So this is my assignment 2 project for using a Steam reviews dataset for sentiment modeling. And I recommend following along with the workbook.html to see the code that I'll be referring to, as that document is sectioned out just as these slides are. So we'll be going through the overview of the predictive task, the exploratory EDA that I did, and some discussion of that, and how I did the modeling, as well as the steps I did for evaluation, and some discussion of related work and my works cited. So to start off with an overview of the predictive task, the predictive task in this project is to classify a video game into one of 3 overall sentiment categories based on the text of its Steam user reviews. So the target labels are going to be positive, mixed, and negative for sentiment, and these labels exist at a game level, not a review level. So to formulate this as a machine learning task, decided to propagate each game sentiment to all of its reviews. So that means we'll be treating each review as an individual training example, and then aggregate review level predictions back into a single prediction per game using majority vote. So in terms of evaluation strategy, because these labels exist at a game level, we'll be evaluating the model at 2 stages. So we'll be doing review level evaluation, which is really more of a preliminary evaluation to distinguish between different classifiers, different models, and game level evaluation, which is going to be our actual goal, since sentiment is a game level construct. And all splits are going to be made at the game level to prevent leakage. And the models, I'll be evaluating them using accuracy, macro F1, which will treat each class equally, weighted F1, which accounts for a class imbalance, and as well as balanced accuracy and balanced error rate, which connects back to the course content, and a confusion matrix to inspect some class behavior. And I think these metrics can be backed up as appropriate because this sentiment prediction problem is an imbalanced 3-class problem. The negative and the mixed cases, as we'll see in the EDA, are minority classes, but they're still important. And macro F1, balanced accuracy, and the balanced error rate will make sure that these classes are able to influence our evaluation. And in terms of baselines, we'll be comparing against just a dummy classifier, naive Bayes, and then we'll be comparing the performance of logistic regression and linear SVM as models. And those baselines are going to allow us to compare performance against just simple models like naive Bayes, and then compare some more linear models like logistic regression and linear SVM, and also understand how review level performance transfers to game level predictions, which again is going to be our actual goal. So in terms of validation and interpreting our predictions, the model will be validated using held out games. So we'll have a game level train and test split. The metrics I described before in terms of evaluation, and a little bit of inspection of misclassification. So this combination of quantitative and qualitative checks is going to balance different types of predictions to make sure that those are meaningful and not representative of any kind of imbalance in the data set. So in terms of the EDA, we have a large Steam reviews data set that we used, and it contains about 12,000 games, almost 8 million user reviews, and various metadata fields such as metascore, hours played, review counts, and some original Steam sentiment labels, which were assigned through various categories. And so a decision I made is to condense those into the 3 categories of positive, mixed, and negative. So in terms of cleaning up the data, that's one of the main things I did is collapse the sentiment labels into those 3 consolidated classes, which does reduce granularity, but it improves the robustness and interpretability of the models and the results, and it makes it a clearer three-class prediction and classification task. So after cleaning up the data and joining it, I got still about 7.7 million reviews. So another thing I wanted to consider in terms of cleaning up the data was filtering out games with very low amounts of reviews, and keeping games with at least a small minimum number of reviews to ensure a little bit more balance. In terms of the training and the test split at the game level, we'll be splitting by game ID, not by individual reviews, and that'll make sure that the same game doesn't appear in the train and the test splits. In terms of cleaning up the review text, I applied some text cleaning, essentially replacing some missing text, stripping white spaces, effectively all the basic pre-processing for tokenization and stop word removal. And I used a TF-IDF vectorizer in the modeling stage to do more of that cleaning. As we can see, the game level sentiment distribution before collapsing into the three labels, it's pretty unbalanced in terms of positive, mixed, and negative. So that was another reason to collapse them into those three categories. Now, in terms of subsampling, purely for feasibility, since it's such a large data set, with some games having tens of thousands of reviews, to keep computation feasible and to prevent just very popular titles from dominating the model training, I capped the reviews per game at 1,000. I capped total reviews at 1 million for training and 250,000 for testing. So we get that 75-25 test split there, and that'll produce a data set that still maintains some diversity across games and sentiment distribution, but it's reducing the influence of large games, so to prevent skew. And in terms of feature engineering, I included hours played, so that's effectively a behavioral signal to reflect how much time a user spent in game, which I thought could be useful for modeling. So to incorporate that, I added log-scaled standardized hours played in addition to the vectorized features. So we have a final feature matrix with both of those, and we're able to filter and cap, as I mentioned before, so that ended up with 1 million training games and 250,000 test reviews. And in terms of some key stats, at the game level sentiment distribution, we did have 7,000 plus positive games, 4,000 plus mixed games, and 900 plus negative games. So we definitely do have that strong class imbalance with positive dominating, but we do have a large scale data set, so I think it will be sufficient volume for training these models. And in terms of the visualizations, there are additional visualizations in the workbook in terms of a few different things that I wanted to explore before I decided on the final inputs, such as reviews per user, just to see how that's balanced, reviews per game, as well as a distribution of hours played, since that ended up being one of the key features that we engineered into the model, and a few other plots, as well as seeing some of the top unigrams in the review text, just to see what was influencing the model the most, since we do have a TF-IDF vectorized data set. And in terms of the metascore and release, those were other graphs that I decided to make. But the important thing at the end of section 2 is that we aggregate reviews to the game level, since that's our objective. And we have a table there just showing the final shape with how many games we'll be working with. Now, moving on to modeling, in terms of formulating it as a machine learning problem, we have the inputs of the review text as represented by TF-IDF, and we have the normalized hours played for each review. So as far as the output, we'll have a label in positive, mixed, negative at game level, and since labels exist at the game level, our pipeline will be assigning each review sentiment of its parent game, training classifiers at the review level, and then aggregating predictions back to the game level using majority vote. And this is consistent with the structure of the data, a bit of supervised text classification, and a sparse high-dimensional feature representation of the data. And in terms of the feature representation, the TF-IDF vectorizer has 50,000 max features, and it's using unigrams, and again, as I mentioned, doing stop word removal in the tokenization. So we also append that log hours feature to form a full combined feature matrix, considering both the review text and the hours played. In terms of the advantages of this approach, I think it scaled pretty well, and it captured word frequency, as well as incorporating the hours played as a behavioral signal in a numeric feature. In terms of the disadvantages, it's somewhat limited in longer range, like context or discourse. Hours played might not be robust in terms of each review. There might be some missing data there, and there wasn't necessarily semantic similarity beyond the unigram overlap. Now, in terms of the models I considered, we have multinomial naive Bayes, which is strong because it's fast, but it does bias towards the majority class, and it ended up having a low macro F1 and a pretty high balanced error rate, especially for the mixed and negative classes. And game level performance actually drops, though it has a stronger review level accuracy. In terms of logistic regression, it's able, a big pro is that it's able to handle class imbalance, and it actually achieves the best game level performance, as we'll see later in the evaluation, and the lowest balanced error rate among any of the models. Some cons are that it's definitely less efficient in terms of speed compared to naive Bayes, and it does still have some confusion between the mixed and positive classes. I also trained a linear SVM, which does have the best review level accuracy, but it doesn't have great balanced error rate, and the game level accuracy does drop, especially compared to logistic regression. So it has some trouble distinguishing some of the more ambiguous cases in the mixed category. Now, in terms of implementation and aggregation, all the models, as I said, were trained on the million training reviews with those features. All of these models are sharing the same train and test splits, so their results are actually comparable. I also had tried some tuning of hyperparameters, but I ended up taking that out because it was pretty inefficient, and it really didn't end up making that much of a difference, so I decided to remove that from my code. So that's just an aside. But at the review level, naive Bayes does have the highest raw accuracy, but it has very poor macro F1, so we're seeing that it's not great in terms of balance. Linear SVM does have pretty strong accuracy at the review level and the game level, but it's got a little bit better balance than naive Bayes, and logistic regression actually ends up being our best as we aggregate. So in terms of the aggregation, I grouped all the test reviews by their product ID, and then for each model, effectively applied a majority vote for the predicted review labels for a given game, and then we're able to compare those predictions with the ground truth. So we got the aggregated game level, as we can see in this table, and we actually see that between the game level accuracies and stats, logistic regression is the winner and showing the best trade-off between accuracy, macro F1, and as we'll see later in section 4, balanced error rate. So in terms of the code, we're able to see all of that cleaning, the encoding, how we selected that subset with 1 million trading reviews, 250,000 test reviews. We're able to see after the global caps how much we had there. And then section 3.3 in the code is the review level. And we can see each of the sections there for each of the different models and the reports. And then section 3.4 is going to give us the final models, which is going to be setting up the TF-IDF representation with hours played as another part of feature engineering. And then we have section 3.4.2 is logistic regression. 3.4.3 is the linear SVM. And then we get the best model from there, and we aggregate. And as we aggregate the model, we eventually see the performance at game level, which is what we can see here, game level. And so moving on to the evaluation section, section 4. As I mentioned previously, I'll be relying on a variety of metrics, so that'll include accuracy, macro F1, weighted F1, balanced accuracy, balanced error rate, and confusion matrix. So I wanted to do this variety of approaches because I know that accuracy alone can be misleading, especially with some unbalanced data like this. So things that we covered in the course, such as balanced error rate, make sure that we have a little bit more accurate treatment of the classes. So in terms of the review level, we kind of covered that already, but the game level, I wanted to go over that a bit more. At the game level, we have naive Bayes with an accuracy of 0.656, linear SVM with 0.686, and logistic regression being the best one at 0.703. And the balanced error rate, logistic regression has the lowest balanced error rate at 0.347, which I thought was relatively low, and a pretty good estimate of how well it was doing. And in terms of the confusion matrix, we see that for logistic regression at the aggregated game level, positive to positive predictions are strong, and they're definitely dominating the matrix here. And we're seeing that the most common error is the mixed category being mislabeled as positive. So that's showing how we collapsed those, I believe it's about 7 or 8 categories into those 3 categories. There is a bit of a fuzzy boundary between those classes in the actual data. And we see negative achieving some of the best recall compared to some of the other classes. So those patterns kind of explain why logistic regression has the lowest balanced error rate, because it's balancing the positive performance with better treatment of the mixed and negative classes than the other models. And then I also just manually kind of did some inspection of the misclassification, and some interesting things that I noticed were that many of the misclassified games have a Metascore of -1, and some of them had fewer reviews, so it made that label noisier. And I saw that mixed games were usually predicted as positive, so that aligns with what we mentioned earlier. And yeah, in terms of the balanced error rate, we see that logistic regression has the lowest one, so that made me pick it as the best one for this task. Now, in terms of discussion of related work, I looked at the papers that were linked on the course website with this data set. I saw some really interesting concepts relating to this task of having this review text and modeling some kind of sentiment. And these papers basically shared ideas about modeling user item interactions, leveraging multi-signal feedback, and architectures that extract information from high-dimensional data. So some parts of that definitely align well with the project that I designed. The paper Self-Attentive Sequential Recommendation by Kang and Macaulay. Effectively, it's relevant because not all signals are equally informative, and so some interactions matter more, and I definitely saw that in not all reviews contributing equally and not all features being as relevant. And so something that I got from that paper was that a future extension could be weighting reviews instead of treating them all as equal during the aggregation, and eventually incorporating some kind of transformer style model, which I experimented with a little bit, but I wasn't getting great performance, so I decided to stick with more robust models. And in terms of this other paper about monotonic behavior chains by Wen and Macaulay, it showed that models, they basically proposed modeling monotonic behavior chains where different user behaviors represented increasing levels of engagement, and they use this model chain rec to show these structured behavior intensities, especially in these sparse settings. And I thought this connected to the dataset that I worked with, because Steam reviews do effectively show one stage in a behavior chain. And though I only used the review text and some parts of the metadata, the paper does kind of suggest incorporating other signals and not just text-based predictions. So that is kind of another idea for extension. And for the final paper, it's about generating and personalizing bundle recommendations on Steam. So that effectively talked about how the groups of games are sold together. And this is somewhat relevant, although I didn't use the bundle data. So I think it's definitely also an interesting idea for extension in the future. And showing how bundles and purchase histories have interdependence. And so a future direction using that could definitely be using those embeddings from the bundles to account for relationships between different games and sentiment. And yeah, in general, those papers kind of talked about weighting reviews through attention, integrating some implicit behavior signals, modeling more relationships between items, like with bundles, and in general, just using more expressive neural embedding models. And here's my works cited. And I just want to say thanks for sticking around for the full time. And yeah, have a good winter break. Thank you.